Okay, so now we're going to get into a discussion of gas stoichiometry. And here's where we're going to combine what we have learned in previous chapters. I think we talked about it in chapter 4 in terms of stoichiometry, and what we learned in this chapter, chapter 5, in terms of the behavior of gases. All right, so the first thing we're going to look at is what is called the law of combining volumes. All right, and this is what the law says. When gases are measured at the same temperature and pressure, are allowed to react, the volumes of the gaseous reactants and products are in small whole number ratios. And what you're going to see is that this term here, the small whole number ratios, is related to the balanced equation. So, for example, if you have a reaction between hydrogen and oxygen to form water, then what you're going to find is that 2 liters of hydrogen, if you start off with that, it will react with 1 liter of oxygen. So there's a clear 2-to-1 ratio between the hydrogen and the oxygen. And the reason why is because if you look at the balance equation, which I'm going to write, I'm going to squeeze it in right here, it's going to be H2 gas plus O2 gas to give H2O. Now, H2O could be a gas or a liquid. I'm going to put gas here, all right? In any case, to balance this, we're going to need a 2 here and a 2 here. So clearly, based on the balance equation, there's a 2-to-1 mole ratio between the hydrogen and oxygen. And that is also true for the volume ratios. There's going to be a 2-to-1 volume ratios between the hydrogen and oxygen, all right? And that's the reason why 2 liters of hydrogen will react with 1 liter of oxygen, all right? Now, the key thing you need to remember is that this is only true if all the gases are at the same temperature and same pressure, all right? So basically, we are assuming that the hydrogen and oxygen and the water are all at the same temperature and pressure. If that is true, then the volume ratios would parallel the mole ratios. Here's another example, the reaction between hydrogen and nitrogen. As stated here, 6.00 liters of hydrogen will react with 2.00 liters of nitrogen to form 4.00 liters of ammonia. And why is that so? Why is it there a 6-to-2-to-4 ratio between the hydrogen, nitrogen, and ammonia? Well, the 6-to-2-to-4 ratio is basically the same thing as 3-to-1-to-2, all right? And if you write down the equation for this reaction, where should I squeeze it? Okay, let me try to put it here. The equation would be N2 plus H2 to give NH3. And to balance this, we're going to need a 2 here and a 3 here, right? So the 3-to-1-to-2 ratio between the hydrogen, the nitrogen, and the ammonia is the same, right? And the volume ratio will be the same, again, provided that the temperature and pressure of all the gases are the same, all right? So the last statement here in this slide says that we do not need to know the actual temperature and pressure. All we need to know is that the temperature and pressure of all the gases are the same. Once that is established, then we can use the volume ratios based on the coefficients of the different gases in the balanced equation. And based on that, I thought we were going to move on to our next example. What this is showing you here is a pictorial representation of the reaction between hydrogen and oxygen to form H2O. And basically, we're assuming that each of these, let me go back to my pointer here. We're assuming that each of these flasks has the same volume. So here we have 2 volume units of hydrogen reacting with 1 volume unit of oxygen, and it's going to form 2 volume units of water vapor, right? So this is just showing you the 2-to-1-to-2 ratio, which parallels the mole ratios that you can derive from the balanced equation, all right? Okay, so here's the example based on what we have just covered. The question says, how many liters of O2 are consumed for every 10.0 liters of carbon dioxide produced in the combustion of liquid pentane, and it gives you the formula for pentane, if all the volumes are measured at STP. Okay, so the first thing we need to do, as is the case for all stoichiometric type problems, is that we need to write down the balance equation for the reaction. So based on the information provided, we can see that one of the reactants would be C5H12, which is a liquid. Oops, sorry about that. Let me try this again. C5H12. Okay, I don't know why this is happening. So let me go back to my eraser, erase all this crap here. Okay, so let's see if I can get this behaving itself. So C5H12, why does this keep happening? C5H12, okay, which is a liquid. Okay, I give up. And then it's going to react with oxygen, which is a gas, to form. Now, you should learn from your previous chemistry experience that whenever hydrocarbon is undergoing combustion, the products are always going to be CO2, gas, and H2O gas. All right? So all we have to do from here is balance this equation. We're going to put a 5 here. We're going to put a 6 here. And to balance the oxygens, that's 5 times 2, 10, plus 6, 16. So we're going to put an 8 here. All right? So this would be the balanced equation. I'm sorry for the mess here. I don't know why this is happening. But basically, we need to start out with that first. Now, the question says that there are 10.0 liters of carbon dioxide produced. So what I would do is start off with the 10.0 liters of CO2, and the question is asking for how many liters of oxygen that reacts. So I'll start off with the 10.0 liters of CO2, and then I would multiply that by a conversion factor. I hate when this happens. Let me try this again. So the conversion factor would allow you to convert from the volume of CO2 in liters to the liters of oxygen. And then the numbers that we would use would be the coefficients for carbon dioxide and oxygen here. So down here, we're going to have 5 liters, and up here, we're going to have 8 liters. And then all we have to do is the math, and that will give you 16.0 liters of oxygen. All right? So that's basically how that is done. Okay, we're going to stop here, and the next topic we're going to talk about is dealing with situations where the temperature and pressure of all the gases are not the same. All right, so this would be a slightly bit more complicated situation compared to what we were just discussing. Okay, until next time.